It's a great pleasure to introduce Davi Obata from the Brigham Young University. He's going to give the first plenary lecture of this afternoon. Welcome. Welcome, Davi.
Okay, thank you. So I just realized that the last time I gave a talk here was 15 years ago during the Jornadas de Iniciação Científica. So I changed a little bit. There were also cameras at the time. So anyway, so it's a great pleasure to be here. I grew up in Rio de Janeiro, so coming back here is already fun, and coming back here for mathematics is even more fun. So I wanted to talk about a joint work with Pablo Carrasco, Radu Saguin, and Brigham Young. And for a good portion of time, I'm going to try to motivate the result and state the theorems. And my goal is really two things. Is one, understand the definition, and two, understand the picture. And if we understand the definition and the picture, I'm happy. And then if we have time, we can understand more things. If not, that's fine. Okay, so if you have a dynamical system on a manifold, so here I'm going to be working with closed manifolds. Let's say we have a volume measure here. If you look at an ergodic measure mu, the basing of the measure is defined as the set of points such that when you look at the Birkhoff average, the limit coincides with the measure. So this is called the basing of mu. So in other words, these are the set of points whose statistical behavior are captured by the measure. And the first important definition is we say that mu is physical if the volume of its basing is positive. So in other words, physical measures, you can think of them as these are the measures you actually see. So they capture the statistical behavior of a set of points that is relevant for the natural measure in the manifold. All right, so now going back to, like grew up in Rio. So I was exposed at a very early age to Palis and Palis conjectures. And one conjecture that has been a source of a lot of inspiration for me, it's one of Palis conjectures. Is that, and I'm going to paraphrase here, it's not exactly how it's written in his paper, but it's that every dynamical system is approximated by systems having finitely many physical measures whose basing of attraction has full measure. In the sense that, in the following sense, so every dynamical system, so you have your, favorite dynamical system. So arbitrarily close to this one, there is another one. And for this one, you have finitely many physical measures. And when you look at the union of their basing of attraction, and you look at the volume of this, is everything. Okay? So Lorenzo mentioned this conjecture briefly in his talk. This conjecture is still open. I think we're far from solving it. But when you look at this conjecture, and I'm stating physical measures. So here I'm stating in terms of physical measures. The conjecture is actually stated in terms of SRB measures, and I'm going to get to them in a little bit. So the conjecture is still open, but there are many things involved in this conjecture. So let's think about problems as a source of inspiration here. The first one is about existence. So existence of physical measures. Another one, finiteness and full basing. And each one has its own difficulties, okay? All right, so a lot of my recent research has been on trying to understand these physical measures, trying to understand their properties, and especially these problems. So like I said, in this generality, like no idea, but maybe we can restrict ourselves to systems with more structure. So we're going to restrict ourselves to partially hyperbolic systems. Okay. But before we get there, let me just give you some examples. So one, well, if you have an axiom A, C2 diffeomorphism. So for axiom A's, you have, there exists finitely many physical measures with the property we want. When you have axiom A's, the no-wandering set, let's just think about a nozzle, for example. So the tangent bundle is decomposed into a stable and an unstable direction. So this thing here gives you two very good properties. One is uniform expansion and contraction, and the other one is those two bundles, they are far from each other. It's not just angle, there's also something called domination there. But you have these two nice properties. And these two nice properties that allow you to build these physical measures by looking at any unstable disk and doing averages on the iterates of this disk. It allows you to control, it allows you to obtain bounded distortion estimates. So if you keep the angles and if you relax a little bit the uniform expansion or contraction, you have works by Bonacci, Viana, and Alves, Bonacci, Viana. Where they prove existence of these physical measures in certain settings, either ES plus E, or, let me put an F here, or E plus EU, where one of these two bundles, they are not uniform. And if you ever heard the names mostly contracting, mostly expanding, that's their setting, or mostly expanding. Okay, so today we want to go to settings where you have directions that are non-uniform and their angles can degenerate. We're going to be really in a non-uniformly hyperbolic setting. Okay. All right, so let me go all the way here, and let's establish our setting a little bit. Okay, so what's going to be our setting? We're going to be working with partially hyperbolic diffeomorphisms, F partially hyperbolic. So this means that the tangent bundle is going to be decomposed into ES plus EC plus EU. We're going to, in today's talk, we're going to be working with center dimension 2. And we're also going to be working with a center bunching condition. And what center bunching means, for now, I'm just going to write here some inequalities. And then later, I'm going to explain what these inequalities are telling us. So if we look at DF restricted to EC, we look at norm over conorm. This is going to be smaller than conorm of DF restricted to EU. Center bunching would also involve another direction of inequality. This one is enough, and that's the only one I'm going to write. Okay? So maybe I'll put here U center bunch. Okay. So Aaron, he has been talking about this uniform expansion or expanding on average properties in the random dynamical systems. Okay, so why of course, like in that world, it's also interesting, but I came from a partially hyperbolic world, so why was I interested in those properties? So let me define that property here in our partially hyperbolic setting. But first, let me state some facts. For simplicity, let's assume that EC, so ECU is integrable, and EC is integrable. So here you have center foliation. Okay, so some facts. Well, we know that EU is always integrable. So you have a nice unstable foliation. So if I pick here 2 points that are in the same unstable, what we can do is we can look here at centers. And we can look at the holonomy map, so holonomy from the foliation. This is going to be a map from, or at least local here, but WCP to WCQ. I only care about the local behavior of this map. And what is this map? I pick a point here, X. I follow its unstable leaf, and I see where it intersects here. This is going to be our HUPQ of X. Okay. So this map, in general, doesn't have to have any good regularity. But when you have this condition here, this map is C1. So we can talk about derivative. So I don't need any. Yeah, this works if you take any transverse. So I'm just using center to make our lives easier. Okay. Okay, so the thing is, this condition here implies that this map is C1, and I don't think I mentioned this. Let's work with C2 diffeos. So here, this map is C1, which means we can talk about derivatives. So we can talk about the linear holonomy. Okay, so what are we going to call uniform expansion? And maybe I'll write here because I'll try to leave this definition here. So we say that, so uniform expanding, and maybe I'll put here on average, and I'm going to call this UEA. So we say that F has this property if there exists a constant positive such that for any point in my manifold, for any vector in the center direction over that point, let's say with norm 1. So let me draw here a picture. I have P. I'm going to look at the unstable manifold. Let's put here a local of P. And here I have a vector in the center, V. Yeah. So what I can do is I can create from this vector a vector field along this unstable using holonomies. So I can create this vector field here, and if I end up at a point Q, what is the vector VQ? This is going to be, I apply the derivative of unstable holonomy of the vector V, and I want to work with unit vectors, so I'm going to normalize it. So this is going to be uniformly expanding on average. And so let's see. If there exists constants such that for any point, any vector, and any, let's say, any R, if I integrate over the unstable disk inside this manifold of radius R, maybe I'll change here, put an R here and a P here, and I look at the log of my dynamics applied to this VQ, and I integrate with respect to the induced Lebesgue measure in the unstable coming from the restriction of our Riemannian metric here in this unstable. So I'm going to put a P here, Q. Well, because I'm not really normalizing the measure, so I'm going to divide by the measure of this thing. I'm going to divide by N. And then I'm going to look at a limit. And I want this to be greater than that constant. So what do we see here? If you forget all of these integrals, we get something that looks like a Lyapunov exponent and is getting closer and closer to Lyapunov exponents. Well, I can say for sure something for every point. So what we do is we are looking at averages. And what we want is that for every point, for any vector in the center, as you average along these unstables, you see growth. You see asymptotic growth, exponential growth. So this is closely related to what the uniform expansion in the future property that Aaron talked about. There is another version of this that looks more like the one, and this condition implies the version that Aaron talked about in the partially hyperbolic world. Okay? All right, any questions on this definition? Yes?
Is there some relation with some hyperbolistic definition of 2011?
Yes, yes, I would just say yes for now. Okay. There's also some relation with this SH property that Luis P. Introduced in a recent paper. Okay, so you can imagine that this thing is giving you some sort of positive exponent somewhere. But I want to work with non-uniformly hyperbolic things. Our center has dimension 2. And kind of the fun case is when you have one positive and one negative. So I'm gonna make an assumption. You don't have to make this assumption for our results, but I'm just gonna make it because it's easier to think this way. So I'm gonna make an extra assumption here for our system is that when you look at the center Jacobian, for every point restricted to, so anyway, the center Jacobian, this is less or equal than 1. This is too strong for what we need. We can do much better than this, but this is enough for today's talk. So let me state a theorem, and then I will tell you about examples. So theorem. So this is joint work with Pablo, myself, Radu, and Brigham Young. And I'm going to put or 5. I think we were aiming for 5, but it's November. So I'll put a 6 there. So I'm going to call this condition star, okay, the condition on determinant. And like I said, we don't need this condition. It's just going to be simpler to state things this way. So if F is uniformly expanding on average and verifies star, then F has finitely many physical measures. So there exist, and they are finite. So let's say mu1, mu k. And let me just say this. Each mu I can be decomposed. So for each I, there exists a ki such that mu I is decomposed into ki measures. They are permuted by F, and Fki mu I is exponentially mixing. So you not only get existence finiteness, but you also get that each of them is exponentially mixing up to a period.
You have a central bounded, may split in 2 directions. It is helps or not?
Can you say that again?
If you have that the central splits in 2 directions,
Uh-huh.
That is good for you, simplify the things, so it's completely relevant.
Not really. So splitting in two directions doesn't imply this property. And I'll explain why.
Doesn't satisfy.
It's not, does not satisfy this property. It doesn't, yeah. And I'll give you examples in a little bit. Okay, so this is the, let's say, the main theorem. That property implies not only the existence, finiteness, you get also very good statistics for those measures. Somehow, I believe that that property is also generic in some sense on partially hyperbolic systems. Okay, now why? So let me talk about examples. And this is actually how I got involved in this business. So the first one that I want to mention is something that I studied during my thesis, which is an example by Pierre Berger and Pablo Carrasco. And let me just say, if you've heard of the standard map, Alejo, he mentioned the standard map in his talk. So this is going to be a partially hyperbolic system on T2 times T2. So let's say, depending on a parameter n. So f on T2, T2. And I'm not going to write down a formula, but let me just say this is a skew product. Coupling the standard map with an Anosov. So meaning there is an Anosov diffeomorphism acting here on this T2. Here we have the standard map, and we do something non-trivial to make this a genuine skew product. And in this system, you have for Lebesgue almost every point. So the center direction is coming from the fibers. So for almost every point, there exists a negative and a positive Lyapunov exponent in the center. So I'm going to put here a C. And it's a genuine, so you have no uniform hyperbolicity here. And it's a genuine two-dimensional center because the standard map doesn't allow you to have a dominated splitting in the center into one-dimensional directions. So you have no uniform expansion, no uniform contraction happening in the center in a non-trivial way. And two, let me say, so in Marcelo Viana's paper, the one that we refer to for Viana maps, there are actually two examples. The first one is the one that is being most studied. It's you're coupling quadratic family with expanding endomorphism on the circle, and you're making a non-invertible skew product. In the second portion of the paper, he also has a skew product where he couples an OMAP. So actually, Viana map. So he's, oh, that's terrible. Let's see here. Coupling an OMAP with solenoid. And in this one, the OMAP, so he shows the existence of positive exponents for almost every point. Because you have strong dissipativeness, that gives you a negative exponent. And the OMAP is also forbidding to have dominated splitting. So this actually, Berger-Carrasco example can be thought of as a conservative version of these Viana maps. Claim these two examples, they verify this uniform expansion on average. I studied this example in my thesis, and then I showed stable ergodicity. And in my proof, I use quite a bit the structure of the standard map. But I always thought that there was something behind the example that made things work. And this is what makes things work, is this property. Actually, all of the examples that are genuine, all of the examples that I know at least, that are two-dimensional center, genuine, non-uniformly hyperbolic with one positive, one negative in a non-trivial way, that I know they verify this property. Let me just mention that there are also constructions of Pablo with Hadoop, with non-compact center, that will verify this property.
Davi, I don't know if you mentioned, is this open, your condition?
I'll talk about this. It's
not open.
It's C2 open, but it's actually C1 open with C2 bounded norm, if you want to be more specific. Okay, so let's see. Theorem examples. Oh, yeah, so let me just mention also another one. Actually, yeah, no. Before I mention another one, let me mention a theorem. And this theorem is going to give the right pictures to have in mind. So theorem, so it's also with Pablo, Hadoop, and Jagan, so I'm going to put here cozy. So this uniform expanding on average property plus star, like I said, we can make star weaker. It's equivalent to, actually I should have defined U-Gibbs measure. So let me write something, then I'll define what that something is, okay? So every U-Gibbs measure mu, and I'm going to define this word in just a little bit. So there exists some gamma positives such that every U-Gibbs measure mu. When you look at the center exponent, the negative one is going to be smaller than minus gamma. And this is going to be greater than the top, smaller than the top one. So you have, they are far from zero. So you have two exponents. Almost every point has an Ozellet stable direction in the center. And I'm going to say this Ozellet stable direction in the center is not invariant by holonomies. So let me just define this word, U-Gibbs. Okay, so U-Gibbs measures. Remember that we have unstable foliation. So U-Gibbs measure, mu is U-Gibbs if it's conditional measures along unstable are absolutely continuous. And so here you have to be, it takes quite a bit of work to actually formalize this because usually unstable foliations are not measurable, so we cannot just disintegrate like that. But you can think of these measures as take any foliated box, and then I restrict my measure. So these are WU leaves. I restrict my measure to this foliated box. Now here, I'm going to write my measure as a combination of measures along these unstable leaves. So these are going to be our conditional measures. And I want that for almost every point, these measures, they are absolutely continuous with respect to the corresponding volume on that leaf. So this is saying that my measure looks nice along these manifolds. The good thing is that this set, the set of U-Gibbs measures in partially hyperbolic setting, it's always non-empty, it's compact, it's convex. In particular, you have ergodic decomposition of a U-Gibbs measure is by U-Gibbs measures. And any physical measure will be U-Gibbs. If there exists a physical measure, it will be U-Gibbs. So this is a good candidate to study when you're trying to understand physical measures, because physical measures have to live here. But these ones, they have better properties to work with. Okay, so what is this theorem saying is that the uniform expanding on average property is equivalent to, when I look at these U-Gibbs measures, I have one positive, one negative exponent. And this condition here says the following. So you pick a typical point P for the measure. I look at its unstable manifold. I wrote there that the measure is absolutely continuous. You actually get better. You get that the measure is equivalent, and you have a good information about the density. So for almost every point here, Q, this point is also going to be typical for the measure. And now I look here at the center. I have my stable at this point. I have here my stable at this point. And I can project this stable direction coming from Mosellad's theorem here by unstable holonomies. And what this is saying is that they don't match. So as long as they don't match, so it's not the invariant by holonomies. Okay? All right, any questions so far?
You mean that this invariance has to fail like locally everywhere?
Mm-hmm. By ergodicity, you can show that if it fails in positive measure, it's going to fail for almost every point. Yeah. Okay, but there is, again, there is this extra transversality happening here because these directions don't match, so they have to twist. I want to draw a picture in a little bit, but first let me just mention one result. And now I'm running out of boards, so I'll erase this one. So pick your, I don't know if that's your favorite Anosov. I don't even know if it's my favorite Anosov, but why not? And consider, let's say, matrix B is going to be a to the power 5, 0, 0, a. So this is going to live in SL for Z. So you have here strong Anosov in T2. So here you're acting by a to the power 5. And in here, you're acting by a. Well, this is an Anosov diffeomorphism, so we have a lot of information. This one is not uniformly expanding on average. Why? Well, in this case, unstable holonomy is just identity between these fibers. So imagine here I have my weak stable direction, so I'm going to put here a WS. And then when I move along unstable, this is always mapping this direction to this table of the Anosov. So when I do average, I'm going to get contraction because it's the stable direction. Okay. So answering your question, here we have a dominated splitting. We even have uniform hyperbolicity, but it's not verifying this property because this table is stuck with the holonomies. But with Sylvain Crevizier, myself, and Mauricio Poletti. So we showed that So here you have B, arbitrarily close to B. So if you look at a neighborhood, arbitrarily close, so it's actually open and dense. You have sets that have this property. We don't write in this using that terminology, but that's what we're proving. Okay. All right, so you can break this invariance by perturbation. In this case, we don't know how to break in general. All right, so now let me draw a picture. So I promised that I wanted to understand a picture. What I really want to do now is I just want to understand what this theorem is actually saying. And once you understand this picture, I really think this picture is quite powerful and it fits many settings, not just this one. But once you understand this picture, I think the proofs, at least we know like what to do next for the proofs.
The idea is that the general situation should be exactly like that, right?
Yeah, should break.
The situation should be generally.
Yeah.
Conjecture.
Invariance of those directions should be rare. Yeah. Okay, let's try to understand this picture here of what this statement is saying. So first, let's talk about projective center dynamics. And honestly, for the rest of the talk, if you wanna keep a picture in mind, think about an Anosov acting here, something weaker acting here. So this one is given a center. And what we're gonna do is we're gonna look at the projective center. So what we're gonna do is we're gonna think about an S1 here. So we're gonna look at the projective center bundle. This projects over M. And we have an induced diffeomorphism there. Assume smoothness for now, just to pretend this is an actually smooth manifold. In general, it won't be because the center will be only holder. And that adds some difficulties, but nothing major. So we have our dynamics here. And there is an induced dynamics here. What is this? Well, if I pick up a point and a direction, I look at the image of the point and the direction obtained by the image of the derivative of that direction. Okay? So we have some new dynamical systems here that projects over the original one, which was partially hyperbolic. And the claim is that there was this condition which I called U-center bunch, which said that we look at derivative restricted to EC, we divide by conorm, and we want this to be smaller than conorm restricted to U. So what is this really saying? Let's think about if you have a point P, we're looking here at ECP. We look at a circle, and then we apply dF to this circle. The circle will typically become an ellipse. And this axis here is going to be the norm. This is going to be the conorm. So this is measuring the lack of conformality that you see in this picture. You can actually put a metric here and say that this quantity is going to give an upper bound on the Lipschitz norm of dF acting on EC. And this is what we're adding when we're looking at this projective. We're adding these circles. So what this condition is actually saying is that, so this condition, U-center bunching, implies that PF is partially hyperbolic. Okay, so let me draw a picture here. So this is our system downstairs. I pick a point. I look at it's unstable. So since this is partially hyperbolic and in fibers over M, so if here I'm adding these fibers, so this is going to be projective centers. And now I pick a point here. This is going to be P in a direction. This is partially hyperbolic. This has an unstable manifold. A projective unstable manifold of PV. This unstable manifold projects here. This unstable manifold is actually coming from holonomies. You obtain this by you pick a point in a direction and you just start to move that with the derivative of unstable holonomies. Okay? All right, so we have this nice fiber system. It's partially hyperbolic, so we can talk about unstable manifolds. Now let me just talk about, I have maybe 3 minutes or 4. So pick a U-Gibbs measure, ergodic. And this measure, so in the conditions of the theorem there, so this measure has a negative and a positive exponent. We can lift this measure to this projective center bundle. And there are 2 lifts. I'm going to call mu plus and mu minus. So mu plus is going to be, over each point, I'm going to consider the Ozelledet's unstable direction over the point. And I'm going to average this with the measure downstairs. And mu minus is going to be the same thing with the Ozelledet's stable direction. Okay, so you have 2 lifts. Imagine here you have E plus, here you have E minus, and over each point, I'm considering E plus and E minus. So you have these 2 lifts. These are the only 2 ergodic lifts of mu. Claim. Okay, so I mentioned this is so now this system here is partially hyperbolic. We can talk about U-Gibbs measure in this partially hyperbolic system. So measures that are absolutely continuous along unstables. They always exist as well. So claim mu plus is what I'm going to call projective U-Gibbs. The unstable direction is always going to be invariant by these unstable holonomies. And what that theorem is saying is that E minus is not. Because E minus, when I start to move along unstables, so let's say this is the unstable of E minus, and E minus is going to jump around. So it's not going to be concentrated in this unstable manifold. What that theorem is saying is that when the uniform expansion on average property is equivalent of, in these new dynamical systems, in this projective center, the only U-Gibbs measures you see there are coming from the top Lyapunov exponent in the center. Once you have this picture, everything really follows. You get, for example, continuity of Lyapunov exponents for restricted to U-Gibbs measures. You get existence of uniform pacing blocks for all of the U-Gibbs measures. One pacing block uniform as every U-Gibbs measure. So you get a lot of really good properties from that picture, or from this picture. So again, one way to think about that property, and that's the way I like to think about this property, is that projectively things are supported on this unstable, meaning the U-Gibbs properties coming from these projective unstables. The stable fails. Okay, so I think I'll stop here.